Tonight, we're going to talk about what happens when something goes wrong in deep space. Not the Hollywood version, where alarms flash, someone figures it out just in time, and the crew makes it home. The real version, where a fire in a sealed atmosphere has nowhere to vent and nothing to stop it from consuming the air the crew needs to survive. Where a life support system failing mid-transit means solving the problem with whatever is on board, because there is no resupply, no replacement part arriving next week, and the signal carrying your distress call won't even reach Earth before the window to act has already closed. Deep space doesn't just make emergencies more dangerous. It changes what emergencies are. On Earth, the word emergency implies a response. Someone coming, help on the way. In deep space, none of that is available at any point, at any stage, for any reason. By the end of tonight, you're going to understand exactly why every emergency out there becomes something the crew solves entirely alone with whatever they have on board or doesn't survive at all. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. There's a version of space exploration that lives in movies and television, and it's a comfortable version. Something goes wrong. Alarms go off. People rush to their stations. Mission Control calls up with a brilliant solution. Someone figures it out just in time. The crew survives. The problem with that version is what it consistently leaves out. It leaves out the light speed delay that makes real-time communication with Earth physically impossible once you're far enough out. It leaves out the fact that a spacecraft carries a fixed amount of everything: oxygen, water, spare parts, medical supplies, food, and when that supply is consumed, it's gone. There's no resupply. There's no restocking. There's no running to the hardware store. It leaves out that certain categories of emergency, once they begin, cannot be slowed down long enough for any outside help to matter. And it leaves out the most important thing of all. In deep space, emergencies don't arrive one at a time. They stack. One problem creates another. The other creates a third. By the time you're dealing with the third, the first one has already gotten worse while your attention was elsewhere. That's what we're going to dig into tonight. Not just the dangers themselves, but the specific geometry of deep space that transforms manageable problems into unsurvivable ones. The geometry of distance. The geometry of commitment. The geometry of a crew that is, in every meaningful sense, entirely on its own. To understand what deep space does to emergencies, you have to look at what changes as you move further from Earth, starting with where humans actually are right now. The International Space Station orbits about 250 miles above Earth's surface. That sounds like a significant distance. And in the context of daily life on Earth, it is. But in the context of space exploration, 250 miles is essentially nothing. A commercial flight from New York to Boston is about the same distance. At that altitude, Earth's magnetic field still wraps around the station, deflecting a significant fraction of the cosmic radiation that would otherwise hit the crew. The planet fills the windows large, close, unmistakably real. And most importantly, if something goes seriously wrong, the crew can be back on Earth's surface in under 4 hours. That is the rescue window. 4 hours. It has defined every protocol, every safety calculation, every decision about what equipment to carry and what to leave behind. The ISS exists inside a rescue window. That changes everything about how you think about emergencies, because it means there's a last resort. It means the training for the worst-case scenario includes the option to leave. Now, imagine moving beyond that. Not to Mars, yet just to the Moon. The Moon sits roughly 239,000 miles from Earth. Light takes about 1.3 seconds to cross that gap. Communication feels nearly real-time, with just a barely perceptible pause. But a physical rescue mission from Earth would take days. The Apollo astronauts understood this with perfect clarity. They were operating without a rescue window. If something went terminally wrong on the lunar surface, no spacecraft was going to arrive in time. Their safety depended entirely on what they carried with them and what they could figure out on their own. Apollo 13 showed exactly what that meant. An oxygen tank exploded in the service module on April 13, 1970. Not a small problem. A cascading failure that threatened the entire mission within minutes. The crew didn't wait for mission control to tell them what to do. They couldn't wait. They were already moving, already assessing, already improvising. Mission control was critical, but they helped by working the problem in parallel with the crew, not by directing a rescue operation. No one was coming to rescue them. The astronauts had to get themselves home, and they were only 3 days from Earth when it happened. Now, extend the distance to Mars. At its closest approach, Mars sits roughly 33 million miles from Earth. Light takes about 3 minutes to cover that distance. A message sent to mission control takes 3 minutes to arrive. Their response takes another 3 minutes to reach the ship. 6 minutes minimum for a single exchange. If you're dealing with a fire, or a pressure leak, or a crew member who needs immediate medical attention, 6 minutes is an eternity. At Mars's farthest orbital position, the delay stretches to over 20 minutes each way. 40 minutes, round trip. A fire that isn't contained in the first few minutes doesn't wait 40 minutes for anyone. Mission control, at that distance, becomes functionally a post-incident review board. They can analyze what happened after. They can advise on what to do next. They cannot help you while it's happening. And this isn't a flaw in the design that better technology can fix. It's physics. The speed of light is the universal speed limit for information. There is no technology, not now, not in any foreseeable future, that makes information travel faster. The delay isn't a solvable problem. It's a structural feature of the universe. And every single emergency protocol for a deep space mission has to be built around the fact that the crew is alone. Every decision, every response, every judgment, call, it belongs entirely to the people on board. There is no one to call. So, now you understand the environment. Isolated from external support. Fixed resources that cannot be replenished. No real-time guidance available from outside. Inside that environment, emergencies hit differently. Fire is one of the most immediate, and it's worth spending real time on because the difference between a fire on Earth and a fire on a spacecraft in deep space is not a matter of degree. It's a matter of kind. On Earth, fire is dangerous, but it's manageable in ways we take completely for granted. You can open a window. You can run outside. You can call for help and have trained personnel arrive within minutes. There are multiple escape routes out of any building. The fire burns, and there are options at every step: evacuate, fight, contain, wait for help. Inside a spacecraft, there are no options of that kind. The ship is sealed. There is no outside to run to. Every breath of atmosphere is precious because it's part of a finite supply, and every fire is simultaneously consuming that atmosphere and producing carbon monoxide and other combustion byproducts that reach lethal concentrations faster than the flames themselves become. Threatening. The Apollo, one fire in January of 1967, happened during a ground test. 3 astronauts, Virgil Grissom, Edward White, and Roger Chaffee, were inside the command module on the launch pad at Cape Kennedy, running through a simulated countdown. A fire broke out in the pure oxygen atmosphere. In normal air, oxygen makes up about 21% of the gas. In that capsule that evening, the atmosphere was pure oxygen at a pressure slightly higher than sea level. Pure oxygen at elevated pressure is extraordinarily reactive. Things that would smolder in normal air burst into flame. Things that would burn, slowly burn, explosively. The fire consumed everything combustible inside the capsule in seconds. The hatch design required pressure equalization before it could open. As the fire built and gases expanded, the pressure inside the capsule rapidly exceeded outside pressure, making the hatch impossible to open from inside. The ground crew outside heard the crew and saw smoke, but the hatch took about 5 minutes to open, even with full effort from outside. By that time, all 3 were gone. And that was on the ground, with the launch pad fully staffed, with support personnel standing physically adjacent to the capsule, with a full emergency response infrastructure at the facility. In space, at full mission pressure, in a suit environment with oxygen partial pressures required for EVA preparation, fire behaves with the same ferocity. But there is nobody outside. No one to hear anything. No hatch that opens to the outside of a building. Just the fire, the sealed atmosphere, and the crew. Modern spacecraft are better than the Apollo 1 capsule was. Atmospheres are mixed gases rather than pure oxygen. Materials are selected for low flammability in oxygen-rich environments. Ignition sources are minimized by design, but fire risk is never zero. Electronics carry current and can short. Insulation degrades over time. Equipment generates heat. Unexpected combinations of materials and conditions create ignition risks that no design review anticipates perfectly. And in space, fire doesn't just threaten the crew through flames and smoke. It threatens every system that keeps the crew alive. A fire near the CO2 scrubbers. A fire near the oxygen generation equipment. A fire near the electrical distribution panels that power everything else. That fire doesn't just burn. It initiates a sequence. And sequences in a closed system, under pressure, don't stop on their own. A spacecraft fire also confronts the crew with one of the most brutal decision trees in all of emergency response. The tools available are limited. Halon, extinguishers for localized fires. CO2 suppressants in some compartments. And in some spacecraft designs, a total flood system that replaces the atmosphere in the affected module with an inert gas, typically nitrogen, to starve the fire of oxygen. Total flood is effective. A nitrogen atmosphere does not support combustion. Fire goes out. A nitrogen atmosphere also does not support human life. Anyone in the module without a sealed suit immediately begins losing consciousness. Before the total flood activates, everyone in the module has to be either in a functioning pressure suit or through the hatch into the adjacent module. If the fire spreads faster than the evacuation timeline permits, if the crew was in sleep period and suits weren't immediately accessible, if the fire started in the module where the suits are stored, if a crew member is incapacitated by smoke before they can get clear, The calculus becomes something that no training document can make clean. You flood the module. You fight the fire with handheld suppressant and risk losing the fight while exhausting what you have. Or you seal the module, accept it as lost, and deal with what losing it means for the rest of the mission. On the International Space Station, a fire serious enough to threaten the crew triggers evacuation into the Soyuz escape vehicles and departure for Earth. The decision is not complicated. You get home. In deep space, the escape vehicle isn't a ticket home. It's a pressurized volume. It's somewhere to be that isn't the burning spacecraft. But it's not a solution. A crew in the escape module is still on the same trajectory. Still millions of miles from Earth. Still committed to whatever orbital mechanics defined when the mission launched. They've reduced their living space. They haven't changed their situation. The carbon dioxide problem deserves careful attention because it is one of the most quietly catastrophic aspects of long-duration spaceflight, and it doesn't arrive with the drama of a fire or the immediacy of a pressure loss. It accumulates. You breathe in oxygen. You exhale carbon dioxide. On Earth, this is irrelevant. The atmosphere is so vast and so thoroughly mixed by wind and convection that the CO2 you exhale disperses and enters the planetary carbon cycle without consequence. In a sealed spacecraft, your exhaled CO2 goes nowhere unless something removes it. At around 0.5%, cognitive performance begins to decline measurably. At around 2%, judgment is noticeably impaired and motor control starts to degrade. At 5% and above, the effects become severe and rapid. Convulsions. Loss of consciousness. A spacecraft without CO2 scrubbing, with a crew of 4, would reach concerning concentrations within hours. On the ISS, there are 2 distinct CO2 removal systems, a carbon dioxide removal assembly that uses zeolite beds to absorb CO2 and regenerate it for downstream processing, and a Sabatier reactor that combines CO2 with hydrogen to produce water and methane. 2 systems, because one failing alone doesn't end you. That redundancy is the difference between a fault and a crisis. For a deep space mission, every kilogram of backup hardware is a kilogram that could be propellant, or food, or spare parts for something else equally critical. Mission architects make agonizing trade-offs. And no matter how carefully they plan, the scenarios they can't fully anticipate are the ones that matter most. The Apollo 13 CO2 problem illustrated this directly. 3 astronauts were using a lunar module designed for 2 people for about 2 days. They needed it to support 3 people for 4. The lunar module's lithium hydroxide canisters for CO2 scrubbing were running low, but the command module used square cartridges, while the lunar module's filter housing required round ones. They were incompatible. Mission Control and the crew improvised an adapter from duct tape, plastic bags, the cardboard cover of a flight procedure manual, and spare tubing. They called it the mailbox. It worked. CO2 levels dropped, and all 3 survived. But they were 3 days from Earth, with real-time communication and rooms full of engineers working the same problem simultaneously. A crew on the way to Mars has a message round trip of 6 to 40 minutes. By the time Mission Control's analysis arrives, the crew has already acted one way or another. The information loop that saved Apollo 13 doesn't exist at Mars distance. Pressure loss is different from CO2 in one critical respect. It doesn't give you time to think. A CO2 buildup is a slow crisis developing over hours. You have time to diagnose, to plan, to implement a response before the situation becomes acute. Pressure loss depending on the size of the breach, can develop in seconds. The atmosphere inside a spacecraft is maintained at roughly 1 standard atmosphere, about 14.5 pounds per square inch. Outside the hull, the pressure is effectively zero. That differential is substantial and continuous, pushing outward from inside against every square inch of the hull. The hull holds it. The hull is engineered to hold it under all expected conditions, tested during manufacturing, inspected before launch. But the hull is also thin. Spacecraft hull material is measured in millimeters. Every kilogram of mass represents launch cost, and hull thickness competes directly with everything else that needs to be on the ship. So the hull is as thick as engineering analysis says it needs to be, not thicker. The interplanetary environment contains particles at a range of sizes. Macroscopic debris, defunct satellites, spent rocket stages, fragments from collisions exists primarily in Earth orbit and is tracked. In interplanetary space, the primary concern is natural particles, micrometeorites, and interplanetary dust. Most are tiny, a grain of sand or smaller, but they travel at velocities measured in tens of miles per second relative to a spacecraft. At these velocities, kinetic energy, which scales with the square of velocity, is staggering even for a small mass. A particle massing a fraction of a gram, traveling at 10 miles per second relative to the spacecraft, carries kinetic energy comparable to a rifle bullet. It hits differently than a rifle bullet, however. Rather than penetrating and tumbling through tissue, it punches through thin aluminum and creates a small hole. The size of the hole depends on the particle. But any hole communicates the pressurized interior with the vacuum exterior. Air moves toward lower pressure, always, without exception. In a large breach, the compartment can depressurize in seconds. In a smaller breach, a pinhole or a crack, the timeline extends, but the outcome is the same if the breach isn't sealed. The immediate response protocol is compartmentalization. Airtight doors closing, sealing off the affected section before the pressure loss propagates to the rest of the ship. This works if the breach is in a section that can be isolated without destroying mission capability. If the breach is in the command module, the primary habitat, the life support bay, the section containing primary electrical distribution, sealing it off, preserves the rest of the ship, but leaves you managing a mission with reduced capability. And someone still has to go outside and fix the hull. Going outside is its own category of risk, with its own timeline, its own constraints, its own ways of becoming worse. Extravehicular activity, EV, what most people call a spacewalk, is one of the most physically demanding and consequentially dangerous things a human being can do. A modern spacesuit is not an accessory. It's a self-contained life support system worn on the body. It maintains internal pressure against the vacuum outside. It manages temperature through an inner, water-cooled undergarment that carries body heat away from the skin, and an outer thermal micrometeorite garment that handles the extreme temperature differential between sunlit and shadow exposures simultaneously. In direct sunlight in space, unprotected surfaces can reach over 250 degrees Fahrenheit, about 121 degrees Celsius. In shadow, negative 250 degrees Fahrenheit, about negative 157 degrees Celsius. The suit manages the crew member's body temperature through both extremes, actively pumping cooling water through the inner garment and managing the outer layer's thermal properties. It supplies oxygen from pressurized tanks, maintains the internal atmosphere at a pressure lower than the spacecraft cabin to allow joint flexibility, about 4.3 pounds per square inch rather than 14.7. This pressure difference between the cabin and the suit is why astronauts must pre-breathe pure oxygen before EVAs. At suit pressure, nitrogen that's dissolved in the blood at cabin pressure would come out of solution if the transition happened too quickly. Bubbles in the bloodstream. The same phenomenon that causes decompression sickness in divers who surface too fast. Pre-breathing pure oxygen flushes nitrogen from the blood, eliminating that risk. The pre-breathing protocol takes a minimum of about 2 hours. In some procedures, longer. This is not a fast process. In a planned EVA, that 2 hours is built into the schedule. In an emergency EVA, those 2 hours are the gap between when the emergency is recognized and when someone can be outside addressing it. During those 2 hours, whatever is failing outside the ship is continuing to fail. Once outside, the suit supports a crew member for roughly 6 to 8 hours before consumables run out. The oxygen tanks have a specific capacity. The CO2 scrubbing system has a specific capacity. The cooling water loop has a specific capacity, all finite, all counting down from the moment the airlock opens. In a planned spacewalk, these limits represent comfortable margins. In an emergency EVA, they represent a deadline. And the Luca Parmitano incident in July of 2013 made the consequences of suit failure viscerally clear. Parmitano was a European Space Agency astronaut on his second spacewalk outside the International Space Station. About an hour into the EVA, he noticed water inside his helmet. Not condensation, actual water, accumulating near the back of his head. He reported it to Mission Control. Initial assessments suggested it might be the drink bag that astronauts carry in the suit, which occasionally leaks. He checked it. The drink bag was fine. The water continued accumulating. It came from the suit's liquid cooling system. A filter had failed, and water from the cooling loop was migrating into the ventilation circuit and collecting in the helmet. In zero gravity, water doesn't drain. It forms a floating sphere. In a helmet, constrained by the shape, it spreads. It covered the back of his head. It reached his ears. His communications became muffled. It crept toward his nose, his eyes. He had to abort the EVA and navigate back to the airlock, largely by feel, because his vision was partially obscured, following the path he'd memorized during pre-EVA preparation. His crewmates, on the other side of the airlock, could talk to him, barely, through the muffled communication, but they could not speed up the airlock repressurization cycle. The cycle takes a minimum fixed time. By the time he was inside and the helmet came off, more than a liter of water floated free into the cabin. He was, within a few minutes, of losing the ability to breathe. This happened in low Earth orbit, with Earth filling the window, with Mission Control watching telemetry in real time, with a hospital 4 hours away, with a crew standing by in the airlock. In deep space, the same suit failure happens to a crew member who is outside because there's a hull breach that needs patching, because the alternative is losing the ship. The communication delay means Mission Control's awareness of the problem arrives with a lag. The nearest medical facility is tens of millions of miles away. The crew member managing the EVA abort is doing so while the rest of the crew is already managing the problem that necessitated the EVA in the first place. The suit failure itself doesn't change. The circumstances around it are entirely different. No emergency in deep space arrives with a clean beginning and a clean end. They bleed into each other. And quiet failures that compound are often more dangerous than sudden obvious ones. The water recycling system starts showing slightly reduced recovery efficiency. Not alarming. within parameters. The crew makes a note, runs some diagnostics, identifies a possible cause, implements a workaround. The efficiency comes back partially, but not fully. They adjust their water usage patterns. 3 weeks later, the CO2 scrubber's performance begins to drift, again within parameters, but trending in the wrong direction. More diagnostics, a filter replacement. The scrubber stabilizes, but at slightly reduced capacity. 2 weeks after that, a micro-meteorite strike. Small. The hull's Whipple shield absorbs most of the energy. But the projectile nicks a coolant line, not a catastrophic failure, a small crack that weeps slowly. Coolant pressure begins dropping. Slowly. The thermal management system compensates automatically, running the remaining coolant harder. The system that was running harder is now running at the edge of its design capacity. At that edge, a bearing in a coolant pump begins to wear faster than normal. 2 months later, the pump bearing fails. The coolant loop loses redundancy. The thermal load on the remaining loop increases. Electronics begin running warmer than optimal. Warmer electronics reduce performance margins. The CO2 scrubber, already at reduced capacity from 3 months ago, begins to struggle with the thermal environment. CO2 creeps upward. Headaches. The crew member who handles scrubber maintenance, who knows that system best, was the one who did the coolant system, EVA, 2 months ago and took a higher radiation dose than planned. They've been noticeably fatigued since then. They're managing it, but they're not at the same capacity they had at mission start. None of these problems is fatal by itself. All of them together represent a crew managing a degraded system with degraded resources, with a crew member operating at less than full capacity, with a mission that still has 4 months to run. When the next problem arrives, and the next problem is coming, because complex systems fail on a schedule that respects nothing, it arrives to this crew in this state. This is cascade failure. It has a structure. It's recognizable. And it's what systems engineers worry about most on long-duration missions. Not the single catastrophic failure, the slow erosion. Radiation exists in a category by itself because it operates without any sensory signal. You cannot see it. You cannot feel it. You cannot smell it. It does not announce itself as an emergency, even as it accumulates. Deep space is permeated by ionizing radiation from 2 primary sources, and they're different in character. Galactic cosmic rays are atomic nuclei, accelerated to extraordinary energies by the violence of stellar events, supernova shockwaves, neutron star magnetospheres, the jets of active galactic nuclei distributed across the galaxy. These particles predominantly consist of protons and helium nuclei, with heavier elements like carbon, iron, and silicon mixed in. They carry energies that particle physicists describe in units called giga-electron volts per nucleon. Some cosmic rays carry energies millions of times higher than the most powerful particle accelerators on Earth can produce. When a high-energy galactic cosmic ray encounters a spacecraft hull, it passes through. The aluminum absorbs some energy and produces secondary particles in the process, a shower of daughter particles that spread from the interaction point. Depending on the hull material and thickness, this secondary shower can actually deliver more dose to the crew than the primary particle would have alone. This is counterintuitive. More shielding of the wrong kind can mean more dose. The physics is well understood. Hydrogen-rich materials, water, polyethylene, are better at stopping cosmic rays without producing problematic secondaries. but they're heavier, and mass is always the constraint. Inside the ship, the galactic cosmic ray flux passes through the crew continuously. Each particle that traverses human tissue deposits energy along its path. It ionizes atoms. It breaks chemical bonds. It can sever a DNA strand. The body has DNA repair mechanisms. Single-strand breaks are typically repaired efficiently. Double-strand breaks, where both complementary strands of the DNA double helix are severed in close proximity, are more difficult. If a double-strand break occurs in a cell that's actively dividing, and the repair is imperfect, the result can be a mutation. Accumulated mutations over time increase the probability of cancer. NASA currently limits career radiation exposure for astronauts to doses associated with a 3% increase in lifetime cancer mortality risk. Estimates for a Mars mission suggest that transit alone, just the trip there, would consume a substantial fraction of that career limit. The exact numbers depend on solar activity and mission architecture, but the constraint is real and recognized. It limits mission duration. It informs spacecraft shielding design. It shapes astronaut selection. Older astronauts have fewer remaining years in which to develop radiation-induced cancers, and their career exposure limits are correspondingly higher. But galactic cosmic rays are the chronic background. Solar particle events are the acute threat. The Sun is not static. Its magnetic field evolves on an approximately 11-year cycle, alternating between periods of relative quiet and solar maximum when activity is intense. During active periods, the Sun frequently releases bursts of energetic particles, protons, and electrons, accelerated by magnetic reconnection events in the corona, expelled in waves that travel through interplanetary space at velocities up to around 1,000 miles per second. A large solar particle event, arriving at a spacecraft in deep space with standard aluminum shielding, can deliver doses that cause acute radiation sickness within hours. Nausea and vomiting, beginning within hours of exposure. Fatigue severe enough to be debilitating. Immune suppression. At high doses, effects on the central nervous system, disorientation, impaired coordination, diminished cognitive function. Mission planning addresses this with a storm shelter, a section of the spacecraft enclosed by additional shielding, where the crew retreats when an event is detected. Water tanks are particularly effective because water's hydrogen content absorbs particles without generating the problematic secondary showers that metal shielding produces. The shelter is not a solution. It's damage mitigation. Crew inside the shelter still receive elevated dose. They just receive less than they would outside it. And here is the scenario that mission architects genuinely lose sleep over. A crew is mid-eva outside the ship, in suits, performing a repair the mission absolutely requires. A solar particle event begins. The monitoring systems detect it. The alarm goes out, and the crew has to abort the EVA and get back inside. The abort sequence, ending the work, making it back to the airlock, cycling through repressurization, has a minimum time that cannot be shortened. The radiation dose delivered to the crew member outside during that minimum time depends entirely on how severe the event is. A moderate event means a bad day and elevated risk. A major event and a slow EVA abort means something considerably worse. And here is the worst version of this scenario. The crew is outside for an emergency EVA, not a scheduled one. They're outside because something requires immediate attention outside the ship. An event begins. They have to choose. Abort and come inside. Accept that the external repair is incomplete. Accept the mission consequences of that. Or finish the repair because the alternative is worse than an elevated radiation dose, and accept what that exposure means for the crew member involved. Neither choice involves calling for help. Neither choice involves waiting for guidance. The crew makes the call. They live with the consequences. Medical emergencies in deep space form their own distinct category because they intersect with a fact that mission planners have wrestled with for decades and never fully resolved. A spacecraft cannot carry a hospital. A Mars-class spacecraft crew might consist of 4 to 6 people. One will likely be a physician. One may have paramedic training. The others may have some medical training as part of their general preparation. But the specific emergency that materializes may require expertise that nobody on board has. Appendicitis affects roughly 1 in 15 people during their lifetime. The appendix is a small structure attached to the large intestine. When it becomes inflamed and infected appendicitis, it causes pain, fever, and, if untreated, rupture. A ruptured appendix releases bacteria into the abdominal cavity. Peritonitis infection spreading through the peritoneum. The membrane lining the abdominal organs develops. Without treatment, peritonitis is fatal. Treatment means surgery. Abdominal surgery requires general anesthesia, a sterile operating environment, a trained surgical team, including at minimum a surgeon and an anesthesiologist, appropriate instruments and suture material, and post-operative intensive monitoring. A spacecraft in transit to Mars has none of these in any conventional sense. It has whatever medical equipment was planned for before launch, weighed and balanced against every other competing mass requirement. It has the medical knowledge of whoever is on board. It has a communication channel to Earth where physicians can provide guidance with a delay of 6 to 40 minutes per message. Surgery in zero gravity poses its own distinct challenges. Blood and other fluids don't pool, they float. Maintaining a sterile field in a shared, pressurized environment where everyone breathes the same air requires different technique than terrestrial surgery. Instrument management is different when objects can drift. Retraction of tissue behaves differently without gravity, providing natural fall. There are ongoing research programs in remote and robotic surgery, in telemedicine for space environments, in developing protocols for emergency procedures in space. This is serious work. It is not yet at the level where any honest surgeon would say they'd accept it without qualification for a major abdominal procedure on a person they cared about. In 1961, a Soviet physician named Leonid Rogozov was stationed at the Novolazarevskaya research station in Antarctica during winter. He developed acute appendicitis. He was the only physician at the station. Evacuation was impossible. The Antarctic winter and weather conditions grounded any possibility of an emergency flight. He performed surgery on himself. He administered local anesthesia, used a mirror, and directed 2 non-medical station personnel to assist. The appendectomy took about an hour and 45 minutes. He survived. He was back on duties within 2 weeks. This story gets cited in discussions of remote emergency medicine as evidence that extraordinary situations produce extraordinary solutions. And it's true. But Rogozov was on Earth, with full gravity, in a heated facility, with continuous radio contact to the outside world under Earth's sky. The conditions were not those of a spacecraft in deep space. The point isn't that a medical emergency in space is necessarily fatal. Crews improvise. Trained people find solutions. The point is that in deep space, a medical problem that would be handled as a routine procedure at any hospital on Earth becomes a test of what the crew can improvise with a fixed set of tools and a finite window before the situation deteriorates beyond recovery. The safety net doesn't exist. The backup doesn't exist. What the crew has is what they have. Temperature in space is counterintuitive enough that it's worth explaining directly, because the failure mode is not what most people imagine. Most people picture space as cold and assume that heating is the main challenge. The reality is essentially the opposite, and it creates its own emergency category. All the electronics inside a spacecraft generate heat continuously. The computers, the life support hardware, the communication systems, the navigation instruments, all of it running constantly, all of it converting electrical energy into heat as a byproduct. The human crew generates heat too. A person at rest produces roughly 100 watts, about the same as an incandescent light bulb. During physical work, considerably more. In an atmosphere, this heat is manageable. Warm air rises, cool air descends, convection distributes heat through the volume, and eventually the structure radiates it away, or air handling systems manage it. In vacuum, convection doesn't work. There's no medium to carry heat away by contact or flow. The only mechanism available is radiation infrared energy emitted from warm surfaces. Every spacecraft has thermal radiator panels specifically for this purpose. The ISS has enormous radiator arrays, the white wing-like structures that extend from the station's truss and glow in infrared from the heat they're continuously shedding. If those radiators fail, the heat generated inside the station has nowhere to go. Temperatures rise. Electronics begin to overheat and fail. The crew's environment becomes uninhabitable. In May of 2013, an ammonia leak in one of the ISS cooling loops came dangerously close to exactly this outcome. Ammonia circulates through the station's cooling system, picking up heat from electronics and interior surfaces and carrying it to the external radiator panels. When the ammonia charge began leaking from one of the loops, that loop's cooling capacity degraded. The sections of the station served by that loop began running warm. Emergency spacewalks were required, too, on consecutive days to replace failed hardware and stop the leak. It was unplanned EVA work performed by crew members who hadn't planned to go outside that day, working on a timeline driven by thermal physics rather than convenient scheduling. It worked. The cooling system was restored. The station remained livable. But the margin was real, and the response depended on having replacement hardware on board, on crew members with sufficient EVA training to handle an unplanned operation, and on real-time communication with mission control that allowed continuous monitoring throughout the repair. A deep space mission dealing with a cooling system failure works within a different set of constraints. Whatever spares were loaded before launch are what exist. Whatever EVA capability the crew has is what's available. Whatever guidance comes from mission control arrives after the situation has already evolved. A cooling loop failure that begins as a small ammonia leak becomes a thermal management problem. The thermal management problem becomes an electronics problem as temperatures rise. The electronics problem becomes a life support problem if the overheating affects the systems managing atmosphere composition. This is cascade, again, and it moves on the timescale of physics rather than the timescale of logistics. Cooling is also relevant to EVA suits in a way that surprises people. The problem of keeping an astronaut comfortable during a spacewalk is not primarily about keeping them warm. It's about keeping them from overheating. A person doing physical work in a sealed suit, working against the pressure of the suit, maneuvering around the spacecraft, handling tools generates considerable heat. In a vacuum, that heat cannot escape by convection. The suit is insulated against the thermal extremes of space, which means it's also insulated against losing the body's own heat. Without active cooling, a person inside a working spacesuit would overheat within minutes. Current suits address this with a liquid cooling and ventilation garment, an undergarment with water-filled tubes threaded through it, similar to tubing in a radiator. Chilled water circulates through the tubes, absorbing heat from the skin. The warmed water flows to a sublimator, a device that exposes a porous metal plate to vacuum, causing water to sublimate, carrying away the heat. This system works well. It's reliable. It's been used for decades. It requires water to work. It requires the sublimator to function. If the cooling system fails during an EVA, the astronaut overheats. There's no external help. There's no way to remove the suit outside the airlock without exposing the person to vacuum. The only option is to abort the EVA and get back inside, which, in an emergency EVA, may mean leaving the repair incomplete, which may mean the hull breach isn't fully sealed, which may mean the cascade continues. Sleep and circadian rhythm are not usually discussed in the context of emergency response, but they should be. Human beings are profoundly affected by light. The circadian rhythm, the internal biological clock that regulates sleep-wake cycles, hormone production, immune function, and dozens of other physiological processes, is entrained primarily by light exposure. On Earth, the 24-hour cycle of sunrise and sunset keeps the circadian rhythm synchronized. On the International Space Station, the station orbits Earth every 90 minutes. That means 16 sunrises and sunsets per day. The light and dark cycle is completely disconnected from any natural rhythm. Artificial lighting is carefully managed to impose a 24-hour cycle on the crew, and this works reasonably well. But sleep quality on the ISS is well documented to be worse than on Earth. Surveys of astronauts show that most sleep less than they'd like and feel less rested than they would on the ground. Many use sleep aids. On a deep space mission, the lighting control is simpler. There's no rapid orbital sunrise and sunset, just the steady, dim light of interplanetary space. But the circadian disruption of months in an artificial environment with no natural light cues is cumulative. Poor sleep quality accumulates. Sleep deprivation, even mild and chronic, has well-documented effects on cognitive performance. Reaction time slows. Judgment degrades. Emotional regulation becomes less stable. Risk assessment becomes less accurate. Complex task performance declines. Military researchers have found that sleep-deprived personnel are often poor judges of their own level of impairment. They think they're performing at normal capacity when performance metrics show significant decline. This is directly relevant to emergency response. A crew 6 months into a mission, carrying accumulated sleep debt, may be less capable at exactly the point where maximum capability is needed. And they may not recognize the impairment. They'll feel like themselves. But the margin that training is supposed to provide, the extra capacity beyond what baseline performance requires, may have eroded to something thinner than either the crew or mission control can measure. The psychological concept of automation complacency deserves attention in this context. Modern spacecraft are heavily automated. Sensors continuously monitor hundreds of parameters. Systems adjust automatically within normal operating ranges. Alarms alert the crew when something falls outside parameters. The crew's role, much of the time, is supervision monitoring, interpreting alerts, making decisions about responses. This is appropriate. The complexity of a spacecraft's systems exceeds what manual management could handle. But supervision of automated systems over long durations produces a characteristic psychological effect. The crew becomes accustomed to the systems working. They develop implicit trust in the monitoring infrastructure. Small deviations that would have commanded attention during early mission phases get classified, consciously or not, as noise. Alarm, fatigue, the phenomenon where frequent alerts, most of which turn out to be insignificant, cause operators to become less responsive to any individual alarm, is a documented risk in complex automated systems. In hospitals, alarm fatigue from monitoring equipment is a recognized patient safety issue. In spacecraft, it's a recognized mission safety issue. The challenge is that the alarm that matters, the one that is not noise, the one that is the beginning of something real, can look identical to the 30 alarms before it that turned out to be nothing. The crew that has been monitoring a well-behaved spacecraft for 5 months may not have the same level of hair-trigger alertness for emergency response that they had on day 1. They're not less capable. They're not lazy or careless. They're human, responding to months of evidence that the systems work and that most alerts resolve without intervention. And when the emergency that is actually serious begins with an alarm that looks like every other alarm, the crew's response in the first 30 seconds may be slightly slower than their training day best, and those 30 seconds may matter. The question of who makes decisions during a deep space emergency is worth being explicit about, because the answer differs from almost any other emergency environment humans have operated in. On Earth, emergency response operates within a chain of command that connects to institutional authority: the incident commander on a fire scene, the medical director overseeing an emergency department, the air traffic controller managing a distressed aircraft. In all of these cases, the decision-makers on scene have access to real-time information, real-time support, and a system that can escalate beyond the immediate responders if the situation demands it. In space, near Earth, on the ISS, on the lunar surface, mission control plays a real-time role in major decisions. The flight director has genuine authority and genuine situational awareness. Major decisions about mission continuation or termination, about resource use, about risk acceptance, are made with real-time collaboration between the crew and the ground. In deep space, mission control's role is advisory. They have telemetry, but it's delayed. They can offer analysis and recommendations, but the crew has already acted before those recommendations arrive. The flight director cannot stop an action in real time, cannot redirect a decision in the moment, cannot override a crew judgment while an emergency is unfolding. The authority for all real-time decisions, including the highest stakes emergency decisions, rests entirely with the crew, operating under whatever command structure exists within the spacecraft. This is understood. It's part of why crew selection for deep space missions emphasizes not just technical competence, but decision-making under pressure. The ability to lead, the ability to follow, the ability to make difficult calls with incomplete information and live with the consequences. but it also means that the quality of emergency response in deep space is bounded by the judgment of a small number of people, operating in degraded conditions without the institutional support structure that normally provides a check on individual decision-making. If the mission commander makes a wrong call, there's no flight director to countermand it in time. If interpersonal conflict within the crew degrades their collective decision-making, there's no HR department or counselor who can intervene in real time. The crew is autonomous in the most complete sense of that word. Both the power of that autonomy and the limits of it belong entirely to the people on board. Resource accounting in deep space is an exercise in existential mathematics. Everything the crew needs to survive is finite. Oxygen, water, food, lithium hydroxide, or equivalent for CO2, scrubbing, coolant, spare parts, medical supplies, power from the reactor or solar panels, propellant for attitude control and trajectory corrections. Each of these has a budget. The budget was calculated before launch. It was designed to be sufficient, with margin, for the planned mission duration. Margin is the word that matters. Margin is the difference between the budget and the minimum needed for survival. It's the buffer against unexpected consumption, unexpected failures, extended mission duration. Every contingency consumes margin. A life support component fails, and the crew has to run a backup at higher efficiency. Margin consumed. A medical situation requires extra water for rehydration or wound care. Margin consumed. A trajectory correction to avoid a space weather event requires extra propellant. Margin consumed. A failed CO2 scrubber cartridge has to be replaced ahead of schedule. Margin consumed. Each individual consumption might be small, manageable, within what the mission planners accounted for. But a mission that lasts 9 months generates a lot of contingencies. Each one draws down the margin a little. And the margin that started generous, calculated to absorb the statistically expected number of problems, is a declining resource, just like oxygen and water. When the margin is gone, the next problem finds no buffer. It finds a mission operating at exactly the minimum. And the minimum doesn't have room for one more thing to go wrong. It's important to understand this at a level beyond the abstract, because the real consequence is often not immediately obvious. Imagine a crew midway through a Mars transit. They've dealt with a minor electrical fault that required rewiring a secondary system. They've had one crew member experience a moderate radiation exposure during a necessary EVA that coincided with an unexpected solar particle event. That crew member is now more fatigued than baseline and is receiving elevated monitoring. The water recovery system is operating at 91% efficiency rather than the planned 95%. They've compensated by reducing shower frequency and tightening water use in other areas. None of these things are crises. Each has been managed. The mission is proceeding. Now, a more significant fault develops in the primary CO2 scrubbing system. Not catastrophic, the backup scrubbing system is available. But the backup system is less efficient. It will handle CO2 removal, but it requires more power to do so. More power means more heat generation. More heat means more load on the cooling system that already lost some capacity when the electrical fault was repaired. The cooling system is now running closer to capacity. Its thermal margins are reduced. the crew works the problem. They implement load shedding, reducing power consumption in non-critical systems to take load off the cooling system. This works. The temperatures come back into acceptable range. But the crew has now reduced operational capacity to manage the thermal situation. Some of the science equipment is offline. Some of the secondary monitoring systems are offline to save power. The mission continues, but in a degraded state. And in that degraded state, the detectability of the next problem is reduced. Some of the sensors that would have given early warning of a developing fault are among the systems now offline to save power. The next problem develops a little farther before someone notices, and the response time is correspondingly shorter. This is the hidden cost of cascade. Not just the direct effects of each failure, but the way each failure reduces the system's ability to detect and respond to the next one. The crews who will go to Mars will know all of this. The engineers who design the missions have thought about it in excruciating detail. The mission architectures try to account for it. Redundancy in the critical systems. Margin in the consumables budgets. Spares for the components most likely to fail. Extensive training for the most likely emergency scenarios. Medical capability sufficient for the most probable medical events. Psychological support protocols. Communication architectures that maximize what mission control can provide despite the delay. All of this is real work, done by serious people who understand what's at stake. And missions will generally succeed. The engineering of human spaceflight has advanced enormously since the early days. Our understanding of the failure modes and the human factors has deepened with every mission. The first crewed Mars missions will be undertaken by the most prepared people who have ever attempted something this difficult, in the best engineered vehicles ever built for this purpose. Most missions will complete successfully. But the structure of the environment doesn't negotiate the probability to zero. There will be emergencies. Some will compound. Some will exceed what the crew can manage. The best preparation in the world reduces the probability. It doesn't eliminate it. And in deep space, eliminated is the only threshold that changes the fundamental equation. Because anything short of eliminated means the crew is, at some point, managing a situation that physics has made unsurvivable. Without a rescue window. Without real-time support. Without the option to abort. With only what they have. There is a dimension to all of this that is harder to quantify, but no less real. And that's what happens to human cognition and judgment over months and years in a confined, high-stress environment with no rescue window. Astronauts on the International Space Station spend roughly 6 months in space for a typical rotation. The station is the size of a large house, multiple connected modules, about 32,000 cubic feet of habitable volume. Earth fills the windows. Communication with family and friends happens in near real time. Fresh food arrives on regular resupply missions. There are psychological support programs, regular consultations with Earth-based psychiatrists and psychologists, scheduled personal communication time, recreational activities. Mission durations have been extending. Some astronauts now spend up to a year. Oleg Kononenko set the record for longest continuous stay in space at about 371 days, completed in 2024. The current understanding of one-year ISS missions is that they're manageable with appropriate selection, preparation, and support. but a Mars mission would run approximately 500 to 900 days from launch to landing back on Earth, depending on the mission architecture chosen. Nobody has spent that long in deep space. Nobody has spent that long in a spacecraft the size of a Mars vehicle, cut off from real-time communication, without the visual reassurance of Earth in the window. The psychological research on confined and isolated environments suggests that cohesion and performance degrade over long durations. Studies from Antarctic overwintering stations, which are among the best analogues available, show that interpersonal friction increases over the winter isolation period. Mood declines. Cognitive performance on certain tasks shows measurable decline. Small irritations that wouldn't register in normal life become significant sources of conflict when there's no escape and no outside. Sleep quality degrades when the normal light-dark cycle is absent. Performance on tasks requiring sustained attention declines in the third quarter of long isolation studies, a phenomenon sometimes called the third quarter effect, where the combination of accumulated fatigue and the recognition that the mission still has significant time to run produces a trough in morale and performance. These effects don't stop missions from succeeding. People manage. Trained professionals with strong motivation and good support find ways to maintain performance even under difficult conditions. But the margin is real. And when emergencies arrive, they arrive to people who are operating within that margin rather than well above it. On Earth, emergency response systems account for human performance degradation through shift schedules, mandatory rest, fresh personnel rotations. The surgeon who's been operating for 12 hours gets relieved. The air traffic controller works a fixed shift with mandatory breaks. In deep space, the crew that launched is the only crew. There is no fresh personnel. There is no rotation. The people who manage the emergency on day 400 of the mission are managing it in the physical and psychological state that 400 days of deep space transit have produced. The cognitive dimension of radiation exposure adds another layer to this. Most public discussion of radiation risk in space focuses on cancer, the long-term probability of developing malignancy from accumulated dose. That risk is real and significant. But it's not the only concern. Galactic cosmic rays, particularly the heavy ion component, interact with nervous system tissue in ways that are qualitatively different from their effects on other cell types. Neurons don't divide. Unlike liver cells or gut epithelium, which continuously replace themselves through cell division, most neurons in the adult brain are the cells you were born with. A neuron lost to radiation damage is not replaced. But the problem isn't just cell death. It's the damage to the molecular machinery that neurons use to function. Heavy ions passing through the dendritic arbor of a neuron, the branching structure through which it receives signals, can damage the receptor proteins and signaling molecules in ways that alter neural circuit function without killing the cell. Research in rodents exposed to the high-energy ions that are a significant component of galactic cosmic radiation shows effects that include reduced performance on maze navigation tasks, testing spatial memory, reduced performance on novel object recognition, testing episodic memory, altered risk assessment and anxiety-like behavior, and structural changes in the prefrontal cortex. The prefrontal cortex is the region of the brain most responsible for executive function, planning, judgment, impulse control, risk assessment, the capacity to remain calm and methodical under pressure. These are precisely the capabilities that emergency response demands. A crew 6 months into a deep space transit has accumulated 6 months of galactic cosmic ray exposure, including to the heavy ion component that research suggests has the strongest neurological effects. The damage doesn't present as obvious impairment. It doesn't show up on a standard cognitive screening. It presents as reduced margin, slightly slower reaction in pattern recognition, slightly less robust executive function, slightly diminished performance at the edge of the crew member's capability. Not enough to be obvious. Enough to matter when the margin is what stands between a good decision and a bad one in an emergency. And this is compounding onto sleep disruption from the spacecraft's light cycle, compounding onto the interpersonal friction of months in close quarters, compounding onto the cognitive fatigue of sustained high-stakes operational work, compounding onto the psychological weight of isolation and distance. The human factors problem in deep space is not a side issue. It is the emergency problem. Because every emergency is managed by humans. And the humans managing those emergencies in deep space are operating under a collection of stressors that has no parallel in human experience. The question of fire suppression in zero gravity deserves more attention than it typically receives, because fire in microgravity doesn't behave like fire on Earth. And that difference has real consequences for how you fight it. On Earth, fire is buoyancy-driven. Hot combustion gases rise because hot gas is less dense than cool air. This creates the familiar shape of a candle, flame narrow at the base, widening and elongating upward as hot gas rises and draws in fresh oxygen from the sides. The fire self-organizes its own oxygen supply through convection. In microgravity, buoyancy doesn't work. There's no rise of hot gas because there's no gravity to drive the density difference. Fire in microgravity forms a sphere. A small, round, blue-glowing sphere with a lower temperature than an equivalent Earth flame. The combustion products, water vapor, CO, two other byproducts, accumulate immediately around the flame rather than rising away. This acts as a partial self-smothering effect. The flame burns cooler and is easier to extinguish in one sense. But it also spreads differently. Rather than following the path that convection creates on Earth upward, a microgravity fire spreads along surfaces wherever oxygen is available. It can follow electrical cables. It can spread through a duct. It can creep along a surface without the dramatic visual signature of rising flames that alerts people to fire on Earth. Early detection is harder. The fire may travel further than expected before it's visible, and the suppression math changes. A CO2 extinguisher works by flooding the area with CO2, displacing oxygen below the concentration needed for combustion. In microgravity, without convection mixing the air, the CO2 disperses differently. A single suppression burst might not distribute as efficiently as it would on Earth. The concentration near the flame might be sufficient, while other pockets of oxygenated air remain in the same compartment. The ISS has smoke detectors and fire suppression systems that account for microgravity conditions. The suppression approach has been refined based on tests. But the crew is trained to respond aggressively and early, because a fire in microgravity that is allowed to develop becomes harder to suppress than its equivalent on Earth. In deep space, the lesson about early response applies even more forcefully. A fire that the crew responds to slowly because the visual signature was subtle, because the alarm looked like noise, because two crew members were occupied with something else, may have consumed more material and released more toxic byproducts before it's addressed. And the toxic byproducts don't ventilate outside. They stay in the air. Toxicity in the enclosed atmosphere of a spacecraft is a hazard that gets less attention than vacuum exposure or radiation, but it deserves consideration. The air inside a spacecraft can become contaminated by things other than CO2, combustion byproducts from a fire, outgassing from materials. Many polymers, adhesives, and insulating materials release small amounts of volatile organic compounds, particularly when heated. Ammonia from a coolant loop leak, bacterial and fungal growth in a moist environment. The ISS has had episodes of elevated formaldehyde, elevated acetaldehyde, elevated CO, all combustion or outgassing byproducts, at concentrations that fell below acute thresholds, but required investigation and remediation. There have been microbial growth issues in the station's water system and on surfaces, requiring periodic disinfection and monitoring. The Trace Contaminant Control System continuously scrubs the station's atmosphere of accumulated volatile compounds. On a deep space mission, the same chemical equilibria exist. Humans in a sealed environment produce metabolic byproducts, shed skin cells, exhale volatile compounds. Materials in the spacecraft outgas over time. The trace contaminant control systems manage this, but they require consumables, activated charcoal beds, oxidation catalysts, filter media. These consumables deplete. If a trace contaminant system degrades, the concentration of volatile organics in the air begins to rise. Many of these compounds, at elevated concentrations, cause effects ranging from eye and respiratory irritation to neurological symptoms. Long-term exposure to elevated levels of certain compounds, benzene, formaldehyde, carries carcinogenic risk on top of whatever radiation exposure the crew is already accepting. This is not a dramatic emergency. It's a slow degradation of the environment. But it's real, and in a confined spacecraft, there's no option to step outside for fresh air. You address the contamination with what you have, or you accept that the atmosphere is becoming increasingly hostile on a timeline that compounds with every other thing already degrading. The human immune system in space behaves differently than on Earth, in ways that have meaningful implications for medical emergencies. Research from ISS missions shows that spaceflight produces measurable immune system dysregulation. Some immune cells become less active. The capacity to fight certain infections is reduced. Viruses that have been dormant in the body, Epstein-Barr virus, cytomegalovirus, varicella zoster virus, which causes chickenpox and shingles, can reactivate. Reactivation of herpes family viruses has been documented in a majority of astronauts on extended missions at rates higher than observed in comparable ground control populations. In most cases, reactivation doesn't produce symptoms. The immune system, though dysregulated, still manages to contain reactivated viruses below the threshold where they cause active disease. But the margin is reduced. A crew member in deep space whose immune system is dysregulated by the stress of the mission, and spaceflight is physiologically stressful regardless of how well the crew manages it psychologically, is a crew member with reduced capacity to fight an infection or to recover from an illness. If an infection takes hold, it does so in a person whose immune response is already compromised. In a spacecraft where everyone breathes the same air, where the confined volume means that the pathogen load, the concentration of whatever is causing the infection, is higher than in the open air of Earth, where the medical resources to treat the infection are whatever was packed before launch, where the physician on board may be treating a patient while also being exposed to the same pathogen and similarly immunocompromised. Infectious disease management in deep space is one of the most underappreciated risks of long-duration missions. Not because space harbors exotic pathogens, because it takes organisms that normally live quietly in the human body or in the spacecraft environment and places them in conditions that favor their activity, in a crew whose defenses against them are reduced. Bone loss and muscle atrophy are the well-known effects of microgravity on the human body. Astronauts on 6-month ISS missions lose roughly 1 to 2% of bone density per month without countermeasures. That's managed through extensive daily exercise, 2 hours per day of resistance and aerobic exercise, specifically designed to load the skeleton in the ways that gravity normally provides. On the ISS, it's managed adequately. Astronauts return to Earth with manageable bone density loss that largely recovers over subsequent months. On a Mars mission, the exercise regimen continues throughout transit. But there's a complication. If an emergency requires suspending the exercise, schedule a significant and demanding emergency that occupies the crew for an extended period, the bone loss accelerates during that period, and there's no catching up by doing more later. Bone loss in microgravity is a physiological process that runs on its own schedule regardless of what else is happening. More importantly, there's an emergency implication in the other direction. A crew member who has been in microgravity for 6 months has measurably reduced bone strength compared to their Earth baseline. If that crew member needs to perform a physically demanding emergency task EVA work, lifting heavy equipment in the partial gravity environment of a surface landing, physical exertion, during a crisis, they're doing it with bones that are more susceptible to stress fractures. Muscle atrophy that has been partially managed by exercise, but not eliminated, means reduced peak strength and endurance during physically demanding emergency response. A crew that arrives at Mars after a 9-month transit is not at the same physical capacity as the crew that launched from Earth. They're managing that decline with the exercise regimen, but the decline is real, and it's relevant to what the crew can physically do when the situation demands everything they have. The planetary protection dimension of deep space missions adds another layer of constraint that complicates emergency response in a specific way. Spacecraft bound for potentially habitable environments, Mars, the icy moons of Jupiter and Saturn, certain other targets are subject to planetary protection protocols. These protocols exist to prevent Earth organisms from contaminating the destination, which would compromise the ability to detect any existing life there, and to prevent potential Martian or extraterrestrial material from contaminating Earth on return. The protocols impose constraints on what biological materials can be on board and how biological waste is handled. In an emergency involving illness or a death, the planetary protection implications affect what options are available. This is not a theoretical concern. Mission planners have genuinely grappled with the question of what happens if a crew member is gone during a mission. The constraints are real, the options are limited, and the crew has to manage an acute psychological crisis while also following protocols designed for a different purpose. This is an area where space medicine, mission planning, and the human reality of exploration intersect in ways that don't resolve cleanly. There are planned responses. They exist in the documentation. None of them are comfortable. And in a real situation, the crew has to execute those responses while also managing whatever else the mission demands of them. The entry, descent, and landing phase of a Mars mission is, by the engineering assessment of people who design these systems, one of the most dangerous periods of the entire mission. Mars has an atmosphere. Not much of one, about 1% of Earth's atmospheric pressure at the surface. That's thick enough to create significant heating during entry. A spacecraft entering at interplanetary velocities heats to thousands of degrees from friction with the thin air. But it's not thick enough to slow the spacecraft adequately, using only atmospheric drag. The iconic description of Mars entry is the 7 minutes of terror, the duration from atmospheric entry to surface contact, during which the spacecraft must decelerate from entry velocity to a controlled landing using a sequence of technologies including a heat shield, a supersonic parachute, and powered descent. All of this has to work in sequence. Each step has to work correctly, and it has to work before the next step can begin, and the whole sequence runs faster than any human reaction time can manage. The EDL, sequence entry, descent, and landing, is fully autonomous. By the time a problem in the sequence reaches mission control, the landing is over, one way or another. The crew has trained for every contingency in the sequence. They have procedures, but the autonomy is complete. No one is flying the spacecraft manually. The algorithms are running. The crew monitors. If something goes wrong, if the parachute doesn't fully inflate, if the powered descent doesn't achieve the right thrust profile, if the terrain at the landing site isn't what the navigation system expected, the crew has whatever margin the system's contingency design provides. And then, the outcome is what the outcome is. There is no go-around. There is no abort to orbit if the landing is going badly. There is the sequence, and the sequence either works or it doesn't. This is the last stage of a journey that has lasted 9 months. The crew has dealt with everything the transit threw at them. They're within minutes of the surface. And they're in a phase where human intervention is essentially impossible, and where everything depends on machinery executing correctly without error. That's the reality of EDL. Not a failure of planning or of human capability. Just the physics of entering a planetary atmosphere fast enough to reach it from interplanetary space. Once on the surface, the emergency dynamics shift, but don't relent. Mars surface operations introduce a new set of risks that don't exist in transit. Dust storms. Mars experiences regional and sometimes global dust storms that can last months. The Opportunity rover was lost in June of 2018 during a global dust storm. Solar power dropped to levels insufficient to keep the rover's systems warm, and it never recovered communication. For a crew depending on solar power for any significant portion of their energy budget, an extended dust storm is a serious threat. Nuclear power on the surface removes the solar dependency. But nuclear systems have their own failure modes. The regolith itself, the loose surface material covering Mars, is fine-grained and pervasive. Martian dust is not like terrestrial dust. It's extremely fine particles in the submicron range and electrostatically charged. It gets everywhere. It coats solar panels. It works into mechanical joints. It potentially contaminates suits and habitats. The perchlorates in Martian regolith, compounds that make up a fraction of a percent of the soil but are distributed widely, are toxic when consumed or inhaled. Keeping dust out of the habitat is important not just for equipment, cleanliness, but for crew health. EVA operations on the surface require careful suit decontamination before entering the habitat. And suits designed for surface operations, which need to handle the abrasive, pervasive Martian dust while allowing the mobility required for surface work, are different from the suits designed for the vacuum EVAs of transit operations. Surface EVA suits have to work reliably in a mildly abrasive, dust-saturated environment. They have to resist the gradual degradation that pervasive fine particles cause in seals, joints, and bearings. And they have to do this over a surface stay that may last hundreds of days. Equipment that can tolerate a few surface excursions may not tolerate hundreds. Maintenance capability for suit systems is critical. And if a suit becomes unreliable midway through the surface stay, the ability to conduct EVAs to go outside for science, for habitat maintenance, for emergency repairs to external systems is compromised. The habitat on the surface has its own vulnerability profile. Radiation is still a concern on the Mars surface. Mars has no global magnetic field and a very thin atmosphere. The radiation environment at the surface is substantially more intense than at Earth's surface, though somewhat better than deep space because the planet itself shields the lower hemisphere. Habitats will likely use regolith shielding, piling Martian soil over and around the structure to reduce crew dose. Getting that shielding in place is early surface operations priority. Before it's in place, the crew is accepting elevated surface dose. The infrastructure of survival on Mars has to be built, in hostile conditions, by people who just survived a 9-month transit and a high-G entry sequence, before the surface environment is really safe for long-term occupation. One particular class of hardware failure that mission planners have extensive documentation on, but that rarely enters public discussion of space risk, is electrical arc faults. A spacecraft's electrical system carries significant power. The primary power on the ISS, generated by the solar array wings, runs at 160 volts direct current. On a deep space mission with a nuclear power source, the voltages and currents depend on the specific reactor and power conversion system design, but they're in ranges where a fault can be catastrophic. Electrical arcs in an oxygen-enriched atmosphere are intensely dangerous. At normal spacecraft atmospheric compositions, an arc can ignite materials that wouldn't normally be considered flammable. Electrical arcs also produce ozone, nitrogen oxides, and other toxic byproducts in a sealed environment. The ISS electrical system is extensively protected circuit breakers, ground fault interrupters, arc fault circuit interrupters. The wiring is inspected, the connections are maintained, but wiring degrades over time. Insulation ages. Connectors develop high-resistance spots from thermal cycling. Equipment that was tested and certified before launch changes over months and years of operation. A wiring fault that develops 6 months into a mission doesn't announce itself with advance notice. It presents as a tripped circuit breaker, or as a sensor anomaly, or as unexplained power draw. The diagnosis requires methodical investigation. The investigation requires crew time. During that investigation, the affected circuit may need to remain de-energized, meaning whatever equipment it powered is offline. If that equipment happens to be something critical, a pump, a heater, a sensor, its absence is felt immediately. The cascade begins. Electrical troubleshooting in the environment of a spacecraft in deep space requires working within the wiring of a system that was designed before launch, with documentation that covers the planned configuration but may not perfectly capture modifications made during the mission or interactions between systems that weren't anticipated. It requires working in microgravity around exposed conductors. It requires making judgment calls about risk, whether to restore power to a suspect circuit, whether to bypass a fault with implications that aren't fully understood, whether to accept reduced capacity in one area to maintain full capacity in another. All of this is manageable. All of it has been done on the ISS successfully. But the ISS is in low Earth orbit with real-time support, with resupply of replacement components on a schedule measured in weeks. On a Mars transit, the same troubleshooting happens with advice arriving 10 to 40 minutes late, with whatever spares are on board, and with whatever the crew knows between them. There is a final category of emergency that is rarely discussed, but that mission planners take seriously, and it involves the crew itself rather than the systems. The possibility that a crew member becomes unable to perform their duties in a way that threatens the mission. Not a medical emergency in the conventional sense. A behavioral or psychological crisis. The selection process for astronauts is rigorous. The psychological screening is among the most thorough in any professional context. People who make it to flight status are, as a population, exceptionally stable. But no selection process filters out all risk. And the conditions of a deep space mission are conditions that no psychological profile was designed against because they haven't existed before. The isolation, the distance, the duration, the loss of real-time contact with everyone outside the ship, the accumulated stress of managing a demanding mission for months, the radiation effects on the nervous system. These are conditions that haven't been tested in humans over the timescales that a Mars mission requires. We have proxy data, Antarctic stations, submarines, ISS missions, but all of those have the fundamental difference that rescue and return are possible on timescales measured in hours to days. A Mars mission crew member who develops serious psychological symptoms, a psychotic break, severe depression that prevents function, a paranoid state that makes them dangerous to the mission, presents a problem that has no clean solution. The other crew members are not psychiatrists. Even the crew physician, with whatever mental health training they have, is managing a person in a closed volume with no option to transfer them to a hospital. The available interventions are limited. Isolation within the spacecraft. Medication from whatever the formulary includes. Telemedicine support from Earth with a delay measured in tens of minutes. The support of the other crew members who are also under stress, who are also affected by what's happening, and who still have to manage the mission. This isn't hypothetical. In Russian Antarctic, overwintering expeditions in the 1960s and 70s, there were incidents of serious psychological disturbance among crew members. In confined environments on Earth, psychological crises occur even among carefully selected individuals. The probability that a Mars mission of 4 to 6 people, lasting nearly 3 years, will include a serious psychological event is not negligible. Planning for this scenario is part of mission design. The scenarios are in the documentation. None of the options are straightforward. And the crew that has to manage a psychological crisis within the spacecraft is managing it, while the mission continues, while the systems need attention, while the other emergencies that arise also need response. It is one more category in which deep space removes the institutional support that normally exists for difficult situations and places the full weight of management on the people who are present. There is a trajectory dimension to all of this that is perhaps the most structurally inflexible aspect of deep space missions. Spacecraft don't operate like road vehicles. You cannot stop on demand. You cannot simply reverse course. You travel on orbital mechanics, precise paths through the gravitational landscape of the solar system. Shaped by the gravitational influence of the Sun and every significant body along the route. These paths are calculated in advance, optimized for the available propulsion, designed to deliver the spacecraft to its destination using the minimum possible fuel. The orbital mechanics of a Mars transit work on the scale of the planetary orbits. Earth and Mars orbit the Sun at different speeds. Earth completes an orbit in 1 year. Mars takes about 1.9 years. The geometry of their orbits aligns favorably for efficient transit. Roughly every 26 months, these are called launch windows, and they're not negotiable. Miss a window, and the next one is 26 months away. The propellant cost of traveling between the planets outside a window is prohibitive for chemical propulsion systems. So when a mission launches, it launches at a precisely calculated moment, on a precisely calculated trajectory, aimed at a point in space where Mars will be when the spacecraft arrives months later. If something goes wrong during transit, the question of whether to abort and return to Earth is not simple. Slowing the spacecraft, reversing direction, and accelerating toward Earth requires propellant. Propellant that wasn't loaded because the mission wasn't designed for that maneuver. Because every kilogram of abort propellant is a kilogram less of something essential to the primary mission. Mission planners do design abort trajectories into mission profiles. These are paths that use solar gravity assist to swing back toward Earth without requiring enormous propellant expenditure. They exist. They're real options for certain phases of the mission, but they have constraints. In the early phase of the outbound journey, roughly the first 3 to 6 weeks, depending on the specific trajectory, an abort trajectory can return the crew to Earth faster than continuing. Past that phase, the geometry changes. The fastest path back to Earth from the midpoint of a Mars transit often curves away from Earth first, using a gravitational slingshot from the Sun before swinging back. The total return time may be as long as, or longer than, the time remaining to reach Mars. This means that past a certain point in the outbound journey, the fastest way home is through the destination. This is a calculated and recognized reality of mission design. It is called the point of no return, and it is not metaphorical. It's an orbital mechanics term, describing the moment past which aborting the mission no longer shortens the crew's time in space. Past that point, every emergency that occurs is resolved with what is on board. There is no option to abort. The trajectory was set. The physics governs. This trajectory commitment has a psychological reality that is difficult to adequately communicate. Consider the crew 4 months into a 9-month outbound journey. They're past the point of no return. They know this. They know it precisely. They've been tracking their position and trajectory continuously. Earth is behind them, growing smaller in the rear cameras. Mars is still months ahead. They are in the longest, most featureless part of the mission. The exciting beginning is behind them. The arrival is still distant. They're in the crossing. Now, a fault alarm sounds. A sensor is reading out of range. The crew goes to work. This might be nothing. Sensors fail. Sensors drift. Sensors give false positives. But it might be the first signal of something real. They diagnose. They find the fault. It's a component in the water recycling system. Not catastrophic, but it requires a workaround that reduces water recovery efficiency by about 5%. 5% less water recovered means 5% more water drawn from the stored supply per day. They do the math. At current consumption rates and this recovery reduction, the stored supply will run short before they complete the return journey. They have to reduce consumption. They implement rationing, and they continue. This is manageable, but it adds a layer. The crew now carries an additional constraint that wasn't there before. Every day for the rest of the mission, water is a concern where before it wasn't. When the next fault alarm sounds 3 weeks later, different system they respond to it, carrying the accumulated weight of that constraint. This is what the point of no return means, psychologically. Not just that you can't go home. It means that every problem you accumulate stays with you for the rest of the mission. There's no resetting. No, leaving the degraded situation behind and starting fresh. You carry it forward. The Apollo 13 survival is often cited as proof that crews can survive catastrophic emergencies in space, and this is true. But the citation is frequently incomplete in ways that obscure what made it survivable. The explosion occurred roughly 200,000 miles from Earth. The crew was, at maximum, about 3.5 days away from the planet when the crisis peaked. The communication delay between the spacecraft and mission control was negligible, under 2 seconds, round trip. Mission control had access to real-time telemetry from the spacecraft. They could see every sensor reading, every system status, continuously. When something changed, they saw it change at the same moment the crew did. The engineering team available to work. The problem included not just the people in the mission control room, but the engineers at contractor facilities across the country who had designed and built every system on the spacecraft. Grumman, who built the lunar module, had teams of people available within hours. North American Aviation, who built the command module, had teams available. The backup crews, the astronauts who had trained for this mission but weren't flying it, were at the facility and available to run simulations. When the mailbox problem arose, engineers had physical mock-ups of the hardware in the building and could prototype solutions before transmitting them to the crew. All of this, the real-time communication, the Earth-based engineering infrastructure, the proximity that allowed near instantaneous support, was what made Apollo 13 survivable. A crew in transit to Mars with the same catastrophic failure has essentially none of those advantages. The communication delay alone changes the character of the crisis. The crew cannot have real-time collaboration with mission control. They cannot receive guidance on how their actions are changing the situation as it evolves. They cannot call up the engineers who designed the failed component and ask questions. They have documentation. They have their training. They have each other. And they work the problem with those resources, entirely independently, because that's what the distance demands. The Apollo 13 analogy is instructive, but not in the way it's usually used. It's not proof that deep space crises are survivable with the right crew. It's a demonstration of what a crisis at Earth proximity requires in resources and support, and therefore a measure of what's absent when the crisis happens farther away. The life support system as a whole is a useful lens through which to see the nature of the risk. Everything that keeps the crew alive: atmosphere, composition, pressure, temperature, water, CO2 removal. Trace contaminant management flows through the life support system. It's not one system. It's dozens of subsystems, interconnected in complex ways, each depending on the others to function correctly. The oxygen generation system splits water through electrolysis. Water input comes from the water recovery system. The water recovery system's operation requires power. Power comes from the electrical system, which requires thermal management to keep electronics from overheating. Thermal management requires coolant loops. Coolant loops require pumps. Pumps require bearings. Bearings where? Pull any thread in this network and it connects to other threads. A problem in one subsystem doesn't stay in that subsystem. It propagates through the connections. The CO2 issue affects the scrubber. The scrubber connects to the ventilation system. The ventilation system affects temperature distribution. Temperature distribution affects electronics. Electronics affect everything. Designers account for this. They design for redundancy, multiple independent pathways, so that a single failure doesn't bring down the whole system. They design for graceful degradation systems that continue to function at reduced capacity rather than failing completely when a component fails. They build in margin, sizing the systems to handle higher loads than nominal operation requires, so that when something fails and the load redistributes, the remaining components aren't immediately overwhelmed. These design choices work. They work well. The ISS has operated continuously for over 20 years through numerous component failures and system degradations, and the crew has remained safe throughout. But the ISS has something deep space missions don't: resupply. When a component fails on the ISS, a replacement can arrive on the next cargo mission. Schedules can be adjusted. Parts can be expedited. The station has been continuously improved and repaired, with equipment and parts that couldn't be there at launch because they didn't exist yet, or because the failure mode wasn't anticipated. A deep space mission carries everything it will ever have at the moment it launches. Every spare part that might ever be needed has to be there on day one. Every tool, every consumable, every material that might be used for improvised repairs. All of it had to be anticipated in advance. All of it competed for mass and volume. And anything that wasn't anticipated, any failure mode, the designers didn't foresee any component that wears faster than expected. Any combination of failures that the redundancy design didn't account for has to be addressed with whatever happens to be on board. Creativity. Improvisation. What the Apollo 13 mailbox was, built of duct tape and procedure manual covers, that creativity saved those astronauts. It will save astronauts again. But it operates within limits. And the limits in deep space are harder than the limits anywhere else. There is one more category of emergency worth examining directly, because it sits at the intersection of all the others and represents the scenario that mission planners discuss in the most careful terms. Call it the contingency of contingencies. Not a single catastrophic failure, a sequence of manageable problems that together exceed the crew's capacity to manage. Real emergencies in complex systems rarely look like the dramatic, catastrophic events that make compelling drama. They look like small failures that go unresolved or that are resolved imperfectly, gradually consuming the system's margin until the system has no margin left. Then the next problem, which would have been easily handled with margin intact, becomes unsurvivable. The Challenger accident in January of 1986 was the result of a known design issue, O-ring performance in cold temperatures that had been observed documented, and discussed in the years before the accident. It was a problem with a known risk that had accumulated without reaching the point of failure. Until the morning of the launch, when the temperature was colder than any previous launch, and the cumulative risk finally reached the threshold. The Columbia accident in February of 2003 was the result of foam shedding from the external tank on launch, a phenomenon that had been observed on many previous missions, damaging the leading edge of the orbiter's thermal protection system. The damage, not properly assessed, meant the orbiter couldn't survive atmospheric re-entry. Both accidents were sequences. Known risks, tolerated, that eventually compounded to the point of catastrophe. In deep space, the sequences don't have the institutional review structure of NASA's pre-launch processing. They don't have the launch commit criteria process. They don't have teams of engineers on the ground who can call for a launch halt. There is no launch halt once the mission is underway. The crew is the assessment. The crew is the review board. The crew decides whether the accumulated degradations are within acceptable margins or not. And they're making those decisions as participants in the situation fatigued, isolated, past the point of no return, carrying the psychological weight of everything that's already gone wrong. Their judgment is the only judgment. And that judgment is operating in the conditions the mission has produced. This is the deepest truth about deep space emergencies. It's not that any individual problem is necessarily unsurvivable. It's that the structure of deep space removes all the external systems that normally prevent individual problems from compounding. Rescue, resupply, real-time support, fresh personnel, the option to abort, the ability to buy time while help comes. Remove all of these, and the crew is the only line between any emergency and its worst outcome. They hold that line with training, with ingenuity, with discipline, with whatever physical and cognitive capacity months of deep space transit have left them. And sometimes, they'll hold it. The engineering will be excellent. The training will have prepared them for the specific scenario. The right person will have the right knowledge at the right moment. They'll survive. And sometimes, the cascade will exceed what's available to stop it. Not because the crew failed. Because the structure of the environment doesn't offer what stopping a cascade requires. Future technology will reshape some of this. Better propulsion is probably the highest leverage improvement. Faster transit doesn't just reduce travel time. It reduces accumulated radiation dose. It reduces the duration of psychological isolation. It reduces the time window in which the life support system has to run without resupply. It reduces the probability of any given failure occurring before arrival. Nuclear thermal propulsion using a reactor to heat propellant to temperatures that chemical combustion can't reach, producing higher exhaust velocity and therefore more thrust per unit of propellant could meaningfully shorten transit times. The technology base exists. Nuclear thermal engines were developed and ground-tested in the 1960s and 70s under programs called NERVA and ROVER. The physics works. What doesn't exist yet is a flight-proven system certified for crewed missions. Getting there requires development, investment, and political will. It's achievable. It's not immediate. Better radiation shielding materials are another active area. Polyethylene and similar hydrogen-rich polymers are more effective than aluminum for blocking the secondary particle showers from galactic cosmic rays. Active magnetic shielding using superconducting coils to generate a magnetic field around the spacecraft, deflecting charged particles. The way Earth's magnetic field deflects them is theoretically possible. The mass and power requirements are significant. But the concept is physically sound. Advanced medical capabilities, robotic surgical systems, AI-assisted diagnosis, expanded pharmaceutical options could change what's possible when someone needs medical attention far from Earth. Closed-loop life support systems that approach true self-sufficiency, recycling atmospheric gases and water at very high efficiency with minimal loss, would reduce the dependence on finite consumables and extend the system's capacity to absorb failures. These improvements will happen on varying timescales, some faster than expected, some slower. None of them are yet in the form they need to be for the first crewed missions to deep space. The crews that go in the next decade will go with technology that is an improvement on what exists today, but not a categorical departure from it. The communication delay will be the same. It will always be the same. Light travels at the same speed. The orbital mechanics will be the same. The human biology will be the same. The basic structure of the emergency problem will be the same as it is right now, just with better tools for managing within that structure. When you understand all of this clearly, the physics, the biology, the engineering constraints, the orbital mechanics, the cascade dynamics, the psychological degradation, what the title that opened tonight means, becomes precise. Deep space turns every emergency into a potential death sentence, not because any individual emergency is necessarily fatal, but because the environment systematically removes the infrastructure that emergency response depends on. The rescue window, gone. The resupply capacity, gone. Real-time external support, gone. The option to abort after a certain point, gone. Fresh personnel, gone. The ability to buy time while help comes, gone. What remains is the crew, the ship, and whatever resources were on board when the mission launched. Every emergency gets managed entirely within those limits. There's no calling for backup. There's no waiting for the right engineer to come on shift. There's no emergency delivery of the part you don't have. There's the crew, making the best decision they can with what they have in the state the mission has left them in. This is not defeatism. It is not an argument against going. The people who will go to Mars, and eventually beyond, will know every word of this. They'll have studied the failure modes, and the cascade dynamics, and the radiation biology, and the psychology of isolation. They'll have run simulations. They'll have trained for the worst cases, and the contingencies of worst cases. They'll be extraordinary people doing an extraordinary thing, and they'll accept the structure of the environment with clear eyes. Because that's what exploration requires. Not the absence of danger, but the willingness to enter it fully informed. The Apollo 1 crew understood the risks of the program they'd joined. Grissom, White, and Chaffee were test pilots who had made careers of accepting calculated risk for things that mattered. The Challenger crew understood that spaceflight was not routine, despite the rhetoric of the early shuttle era. The Columbia crew went, knowing what they went, knowing. The people who will go to Mars will go knowing what we know now, that the environment is hostile in ways that are structural, not incidental, that the emergencies that come will come without rescue, that the cascade potential is real, that they are the only resource available, and they will go. Because the question that deep space poses, whether life can extend beyond the single world it arose on, whether intelligence can fill more of the universe than one thin biosphere on one pale dot, is a question that certain people feel compelled to help answer. Even at the price, the answer asks. What they carry into that void, more than any supply or any tool, is the understanding that there is no calling for help. There is only what they know, what they have, what they can do with it. That has always been the contract with the frontier. Space is simply the largest frontier there is, and the people who choose to enter it with full awareness of what it demands are something the word remarkable doesn't quite cover. Thank you for spending time on this with me tonight. The universe is extraordinary, and so is the scale of what it demands from anyone who chooses to enter it deliberately. If tonight left you thinking about what human exploration actually costs, not the achievement, but the structure of the risk, then take a second to like the video or subscribe. It helps this channel keep going and keeps these conversations reaching people who think about them seriously. Good night.